Welcome back to The Explainer. Today we're unlocking the secrets of a machine that literally powers our modern world. But we aren't just looking at a hunk of metal today, we're looking at the stage for an eternal, invisible chase. I'm talking about the AC Induction Motor, a device where brilliant engineering meets the fundamental laws of physics.
Okay, let's dive right into this. We'll start with the rotating magnetic field, look at the anatomy of the motor, explore the infinite chase known as slip, tackle rotor frequency and reactance, and finally, wrap it all up with the equivalent circuit.
Section 1. The rotating magnetic field.
Before we even touch the physical nuts and bolts of the motor, we've got to understand the invisible ghost running the entire show. A rotating magnetic field is a magnetic field with a constant magnitude, produced by balanced three-phase windings mechanically displaced 120 degrees from each other. That part right there, the 120-degree physical displacement, that is absolutely the secret sauce to making the magic happen.
Look at how the three specific vectors inside the stator, labeled BA, BB, and BC, are physically arranged in a perfect circle. They're separated by exactly 120 degrees. This exact mechanical geometry forms the absolute foundation for everything we're talking about today.
Now, what happens when we connect that physical setup to electrical power? Well, imagine three continuous sine waves representing our balanced three-phase source over time. As these waves peak and crash, they pump electrical current into those perfectly spaced physical windings. It's this beautiful dance between electrical waves and physical geometry over time that actually creates the rotation. Okay, don't let the vector math intimidate you here. You absolutely do not need to memorize these trig identities. The crucial part is the result at the end. All this math proves is that when you combine those three phases, the resulting magnetic wave doesn't just awkwardly pulse or wobble. Instead, it stays at a constant magnitude, exactly 1.5 times the maximum, and it just spins endlessly in space. We've essentially conjured up a perfectly smooth, invisible, rotating magnet.
Now, what's really interesting is how we can easily calculate and control the speed of that invisible spinning magnet, what we call the synchronous speed. There's a direct inverse relationship between the number of poles in the motor and its synchronous speed in RPMs. So if you double the poles from, say, 2 to 4, the speed drops by exactly half. It's a remarkably simple but super powerful way engineers customize motors for entirely different jobs.
Section 2. Anatomy of the motor.
All right, let's move from that theoretical magnetic ghost to the actual physical hardware that responds to it. In real-world stator construction, you've got a heavy steel frame supporting the core. But notice, the core isn't just a solid chunk of metal. It's built from thin, stacked laminations, which is absolutely brilliant for reducing energy loss. And all around the inside are evenly spaced slots. That right there is exactly where those three-phase windings we just mapped out are housed.
And sitting right inside that stator is the rotor. Now, there are two main flavors here. First, the squirrel cage rotor, which, no joke, literally looks like a metal hamster wheel. It uses aluminum bus bars shorted together at the ends by aluminum rings. Then, you've got the wound rotor, which uses a full set of three-phase windings connected to slip rings on the shaft. But here's the massive takeaway for both. They are essentially short-circuited, and that's completely deliberate. It allows an induced current to flow freely, which then creates its own secondary magnetic field.
Section 3. The infinite chase. Slip.
Everything we've talked about sets the stage for an eternal, looping chase between that physical rotor and our invisible magnetic field. But let's pause for a second. Can the induction motor ever actually run at the exact synchronous speed of the magnetic field? Think about it. What would physically happen if that chunk of metal in the middle finally caught up to the magnetic ghost it's chasing?
Let's walk through the chain reaction step by step. Imagine the rotor actually hits synchronous speed. Suddenly, there's zero relative motion between the invisible field and the physical rotor. They're moving perfectly together. Because of that, the magnetic flux lines aren't being cut by the rotor bars anymore. No cutting means zero induced current in the rotor. And zero current? That means zero torque. The motor literally loses its power immediately, causing the speed to drop right back down. It's this wild paradox. Actually, catching the field destroys the very force that was pulling it forward in the first place.
And this is exactly why we have slip. Slip speed is that crucial difference between the synchronous speed of the magnetic field and the actual mechanical shaft speed of the motor. You guys, slip is the very thing keeping the motor alive. It's the gap in the chase. It's that constant state of falling slightly behind that ensures magnetic lines keep getting cut, current keeps getting induced, and torque is continuously generated. Let's look at the mathematical extremes for a second, starting with S equals 0. If slip is 0, the rotor is running at perfect synchronous speed. But, as we just learned, that means no flux lines are being cut, absolutely no torque is produced, and the motor fundamentally fails its objective. It just coasts along until it slows down again.
Now, on the total opposite extreme, what if S equals 1? That means the rotor is completely stationary, like it's physically blocked from moving. The magnetic field is just whipping past it at full speed, inducing maximum voltage, but the shaft is completely stuck. In this state, the motor basically acts exactly like a short-circuited transformer, and it draws massive amounts of current.
Section 4. Rotor frequency and reactance.
Let's move along and see how this whole concept of slip physically alters the electrical characteristics inside that spinning rotor. Look at this relationship. Rotor frequency equals slip multiplied by the supply frequency. Now, because the physical load on a motor is always changing, maybe it's hauling a heavy elevator, or maybe it's just spinning a fan, the slip is also constantly changing. And because the slip keeps changing, the frequency of the voltage induced inside the rotor is completely variable. It is quite literally a moving target.
And here is the domino effect of that. In AC circuits, reactance changes with frequency. So, as our slip inevitably changes the frequency, the rotor circuit's reactance changes right along with it. The rotor reactance becomes the slip multiplied by the baseline blocked rotor reactance. So we've got a seriously tricky math problem on our hands. The voltage is changing, the frequency is changing, and the reactance is changing, all tied back to this single shifting variable of slip.
Section 5. The equivalent circuit.
Okay, we're now going to solve that massive mathematical headache we just uncovered, so engineers can actually model and predict this motor perfectly. Here is our initial very messy reality, the rotor current equation. Notice how our slip variable, S, is infecting both the top and the bottom of the fraction. It's sitting up there in the voltage numerator, and it's completely tangled up down below in the reactance denominator. Trying to model any circuit where both the voltage source and the internal impedance are just constantly fluctuating, yeah, that's incredibly difficult.
So, the crucial point is how we fix it. And honestly, it's beautifully simple. We just mathematically divide everything, top and bottom, by the slip, S. By doing this, the S completely cancels out on top, which gives us a nice, stable, constant voltage. It also cancels out on the reactance down below, giving us a stable reactance. All of that variation, all the messy reality of a spinning, dynamically changing motor, just gets mathematically shifted onto a single imaginary variable resistor. It's genius.
And boom, just like that, the induced voltage problems solved. The varying frequency problems solved, because we've mathematically stabilized the rotor. The stator and rotor circuits can now be seamlessly combined into one single equivalent circuit. We literally took a wildly dynamic, spinning, chasing machine and mathematically froze it into a simple, stable, stationary electrical circuit. It's an absolute engineering triumph for sure.
Which brings us to the end of our journey for today. But I want to leave you with a bit of a provocative thought. We've seen that slip is essentially an energy loss, right? It's this constant falling behind that absolutely forces the motor to function. But looking forward, how might future engineering completely eliminate this infinite chase without sacrificing the massive torque that powers our modern world? Something to think about. Thanks so much for hanging out and focusing today. Keep questioning, keep learning, and we'll catch you on the next explainer.